Hello and welcome back. Let's continue our foundation engineering class. We are on this chapter number 3, shallow foundation, ultimate bearing capacity. I think in the previous video, we covered the general formula, the formula of ultimate bearing capacity, depending on the type of failure, general shear failure or local shear failure. Okay, so we did this for several type of shapes, foundation shape, strip footing, square foundation, and also circular footing. This is what we did last time. And we discussed about safety factor of also in the previous video. Okay. So we will continue in the same with the same estimated formula equation of ultimate bearing capacity. But this time we will bring up the effect of water table. Okay, how this equation of bearing capacity will be modified due to the presence of water. Okay, this is what we are going to discuss in this video. So part 5 of this chapter, modification of bearing capacity equations for water table. So as I said last time, we saw this. This is just a reminder. In case of general shear failure happening in the ground, we have these 3 bearing capacity formulas. This one for the continuous or strip foundation, this one for square foundation, and this one for circular foundation. In case of local shear failure, these are the 3 bearing capacity equations we have. Okay, this is just a reminder. So all these 6 equations are when the water table is very far from the footing base. Okay, there is no water, or the water is very far from the foundation. Okay, I will put this one of these formulas here, this equation. So as I said, those equations give the ultimate bearing capacity based on the assumption that the water table is located well below the foundation. Very deep, the water table, water level is very deep. Okay, this is the assumption. The 6 previous formula, all of them, the 3 for the general shear failure and the 3 for local shear failure. Okay, what about now when we have, if we have the water table near the footing, near the foundation, what will happen? Okay, if the water table is close to the foundation, some modification of the bearing capacity equation will be necessary. We have to modify this, the 6 formula we show. Okay, here is illustration. This figure will help us to deal with this. For example, we may have the water table here, just here. Okay, in this case, what will happen? How will we modify these equations? Or sometimes we have the water table here. Okay, what will happen in that case? So we have maybe 3 situations, 3 cases we will discuss in this video, in this lesson. Okay, so the first case, when can you see D1? What is D1? D1 is the level of the water table, mean from the ground surface to the water table, the level of water. Okay, this is D1. Okay, so if D1 is between 0 and DF you know already, I think DF is just the embedment, from the ground surface to the base of the foundation of the footing. This is DF. We defined this before from the beginning of this chapter. So if the water table is between this, like this, it can be here or here or here. Anyway, just above the base of the footing, what will happen in that case? Okay, remember that this bearing capacity, this equation for the bearing capacity, this one is for the strip footing, but what matters here is the shape, the the, the different part of this equation. As you know, the only difference is just some coefficients. Okay, this is the contribution of the cohesion. This is contribution of Q, the charge, the overburden pressure. Okay, and this is the contribution of the gamma, the ground beneath the foundation. I told you this before, I think. This is this gamma, this gamma here and the n gamma here are the gamma of the soil beneath the foundation. Please remember that. Okay. So DF, this Q is the charge, which is just DF multiplied by the gamma of this soil. So if you have this situation, how will we modify the bearing capacity? The thing we have to modify, of course, will be this Q will be modified because the overburden pressure will not be same. It will be this. We have to look for effective discharge charge. Okay. Remember this Q was only DF multiplied by alpha. Okay. I will go back in the previous slide to show you that. In this slide, you see, we said, or maybe in the previous video, not this one. But anyway, I think you understand that it is here. Okay, you can see that previously Q is just gamma multiplied by DF. That was the value of Q. This Q in this formula, you see, we have Q here, we have this Q, we have this Q, we have Q here. But once we have water here, the weight, because this Q is nothing but the weight of the soil above the foundation, the footing level. Okay, just the weight of this soil. Please remember that. It's easy. And to have the weight, just multiply the unit weight by DF. Okay, but in this case, okay, let's go back to where we left. Here. We left here, yeah. So in this case, if you do DF multiplied by gamma, it will be wrong. Because now, because of this water level, you have two type of soils. Let's say this one is saturated and this one is unsaturated soil. But the philosophy, the concept is same. We just want the weight of the soil above the foundation level. What is that weight? So the only thing you have to do is divide this by two, like two soil layers. This soil layer from here to here, that one is not affected by the water level, by the water. It's so similar to the previous one. But you have to know the thickness of that. And this is D1. So D1 multiply the gamma here. Maybe it was better if I write gamma here. Okay. But anyway, you know that this part is not affected by the water. So the weight of this part, this thickness, is D1 multiplied by gamma. This is what is here. Okay. Then we have to plus the weight of this soil. Okay. The weight of this soil. As you know, water is helping to support load. Water is helping to support load. Okay. The weight of the water this soil, saturated soil itself, is heavier than the one here. But the stress that this will cause will be partially supported by the water. That's why here we have to do the gamma sat is the saturated unit weight of the soil here. You have to take that one minus the unit weight of water and multiply it by the thickness of this layer. Then you have the weight, the contribution of this layer. Okay, so D1 and D2. Okay, I hope it's very clear for everyone. So you have to divide this, the above, the ground above the foundation level, to two parts. Okay, the part that is not saturated and the saturated part. Okay, for the saturated, the unsaturated part, the part above the water level is multiplied by the original unit weight. That is this one, D1 by gamma. Okay, plus now this depth, the part that is saturated, multiply it by this gamma sat minus gamma W. Gamma sat, you know, the gamma, the saturated unit weight of this soil. For example, you have, if here it was maybe 18, here it will be maybe 20. Okay, so in gamma W, you know already, it's 9.8, something like. Okay, so next, what you have to consider is this part, the last part of the equation, the formula. As you remember, I said that this gamma here is the gamma of the soil beneath the foundation level. I said that for the beginning of this chapter. So what will happen to this gamma then? Because as you can see, the water level is way beyond this. Okay, this soil is also saturated. So what you have to do in that case? Okay, so this is just explanation. Gamma sat is the unit weight of saturated soil. Gamma W is unit weight of the water. Okay, so this part now, this gamma, okay, the value of gamma in the last terms, in the last term of the equation, what does it mean even? The last term is just this part, because the equation has three parts: first term, second term, last term, third term. This part, this term is what we are talking about here, for you to see it clearly. Here, this part is what we are talking about. Okay, so the gamma here has to be also changed. Okay, you should replace it by same gamma sat minus gamma W. Okay, the same, as you can see, it's same here, right? But this is supposing that the soil is uniform. Okay, the gamma sat of this place minus gamma W. So this, in this equation, you have to replace it by that. Is that clear for everyone? Okay, I sometime you have, if for example, supposing that the gamma sat here of this soil beneath this level is different, as I said, sometimes the soil here is different to the soil here. In that case, the gamma sat here will be different to gamma sat here in this zone. So the gamma sat you see here in this equation is not always equal to the gamma sat here. But in case of uniform ground, yeah, it's same. Okay, so this is what we have. So this is first case. Next, second case. What about if we have now the D0 small d? What is small d? This one. Can you see this? D is here. I mean, the water level is this case now. Okay. This is second case. Case number 2, the water level is below the foundation level. But how below? Is it very deep below, or below but near the foundation? So if we have this case, for example, D, you can see the water table is below the foundation level, right? But how below? This distance D, it means the distance between the foundation level and the ground water table is what we should monitor in that case. What is this difference? What is this distance? If this distance is less than B, less than the B is the larger, the width of the foundation. If this distance is less than B, we have to treat the problem differently. But if this distance, this one, is larger than B, then it will be treated differently also. So the first case we will treat, this is case number 2 here, corresponding here, is when this distance is less or equal to B. B is the width of the foundation. Okay, here is what we are going to do in that case. First, this Q, it becomes similar to the original one. Okay, because in that case, if the water table is here, you can see that the soil above the footing level is not affected by water, right? It is dry soil, so we don't have any water problem in that case. Okay, please consider water level is now here, not here. Okay, it means all soil, everything above here is dry, so we don't have issue with water. So in that case, the Q here, this one, will be just gamma multiplied by DF, same DF here. Finish, no problem. But what will happen to this one, this gamma? Because the water table is here, it beneath, we have two zones. In that case, this zone non-saturated and this zone is saturated. The non-saturated zone, the thickness is less or equal to B. So this gamma in this last term of the bearing capacity equation must be replaced by this equation. This is what we have. Okay, replace it by this. So gamma prime plus D divided by B. What is D divided by B? B is here, right? D is here. And gamma minus gamma prime. Gamma prime, you know, right? The soil mechanics class. It is similar to the gamma minus gamma of water. Okay, this is gamma prime. Okay, so this is when we consider that the modification, we assume that there is no seepage force in the soil. If there is no seepage force in the soil, we can assume this modification. So gamma prime plus D divided by B and gamma minus gamma prime. In that case, the gamma will be the dry gamma, okay? Then this gamma prime, I said it gamma saturated gamma, minus gamma of water, like in the previous case number 1. Okay, so this is what this is what we have as modification. Okay, the modification you will bring up when you have water table in the ground, depending on the location of the water table. There is still last case left. So the last case is when now we will have D, this one, the distance D is larger than B. Okay, this is the last case we will see. So case number 3, okay, when the water table is located so that D is much larger, it should be larger, strictly larger than B. Okay, this one is higher than the width, the larger of the foundation. In that case, we will consider that there is no effect on the ultimate bearing capacity. Okay, so that will be all for this. So remember, we have 3 cases. First case, let me go back again. First case is when the water table is here. In that case, you need 2 modifications. You modify the Q, replace this Q by this equation. Okay, gamma sat minus gamma W is what is gamma prime actually. This is gamma prime. Okay, D1 by gamma, D1 is this. So it means you need to know the depth of the water table, multiply it by the unit weight of this soil. Okay, plus D2 is this one. From the water table now to the basis, the foundation level, multiply it by this gamma prime. So this will be replaced by, this will replace this Q here. Okay, this is the first modification. Second modification is this gamma here, replace it by gamma prime. The gamma prime is defined here, gamma prime, gamma sat minus gamma W. In this first case, these are 2 modifications are needed. The second case is one when the water level is below the foundation level, but it's not too much below. It's below, but still close to the foundation level. And the distance is less or equal to B, the foundation width. That means in that case, the only modification you need is this one, because this Q here is the same as the previous formula we said, the previous equation. Okay, so the only modification in this case is replace this gamma by this gamma bar. It's gamma prime. I told you gamma prime is gamma sat minus gamma W. Okay, this gamma is the same gamma, dry gamma, minus gamma prime. Okay, so this will replace by this one, will be replaced by the all this. This is the only modification we have in this case. But if now we have the water level is deep, the depth of water level is larger than the footing dimension, then you don't have to do anything. No modification needed in that case. Do you understand? I think. So this is how water table, the location of water table will modify the bearing capacity equation. But remember, all the coefficients that we saw before, that those coefficients remain. Okay. So if you go back in the sixth equation we gave for strip footing, square footing, circular footing, and depending if you have general shear failure or local shear failure, those coefficients are still the same. The only thing that is changing, you see that it is only this Q or this gamma, that's all. Okay. So thank you very much for this. We will stop here and we'll continue next time. So thank you for your time and see you very soon.